Let's look at surface area of a surface of revolution. So we start with some function in 2 dimensions. So this right here is my f of x. And I'm looking at it from some point A to some point B, and I'm going to revolve it around the x-axis here. Now, think about our arc length. Arc length involves these little diagonal lengths that we collect. In this case, I'm taking that little diagonal length and I'm revolving it with the radius here. The radius here happens to be the function value. When you rotate something like that, and you look at what's happening with the edge of it, then you're going to end up with the circumference of a circle. So you can see here I have this 2 pi times f of x. So that's the circumference of the circle I'm making. And I'm making that circle with this little diagonal chunk, which is like a piece of a cone is what I'm generating. So I have all these little segments of cones I'm generating. A segment of a cone is also called a frustum. And the area of the frustum evolves, a bunch of them evolve into this integral here, which is basically the arc length chunk times that circumference of the circle that we're building. And so we're going to figure out how much paint I would need, say, for a shape that looks like that, if that was the original curve that I revolved. Let's give it a try. So we'll just do it for a line segment, which is going to make a chunk of a cone, and a chunk of the cone with the top chopped off is called a frustum. So here I need to know what is f prime. So f prime is simply just 2 in this case. So then I want the integral as x goes from 2 to 4 of 2 pi times my function 2x plus 4 times my arc length formula, 1 plus the derivative squared, which is just 2. Fortunately, that ends up just being a constant. Sometimes these can be pretty tough integrands to find an antiderivative for, but this one's not bad. 4 plus 1 is 5, so I have the square root of 5. So cleaning this up a little bit, I can pull out a 2 pi square root of 5. Now, I could also factor a 2 out of the function, but I'm not going to worry about that. So essentially, I have this constant times my function here. And that's not bad to find an antiderivative for. So we get our constant 2 pi square root of 5. The antiderivative we'll put in a square bracket. So antiderivative for 2x is x squared. Antiderivative of 4 is 4x. And that antiderivative is evaluated from 2 to 4. So continuing this before we whip out a calculator, we're going to get 4 squared, or 16, plus 4 times 4 is 16, minus 2 squared is 4, plus 2 times 4 is 8. So that's going to give me 32 minus 12, or 20. So altogether, it looks like my surface area is 20 times 2. We can call it 40 pi square root of 5. And you could check this by looking up the formula for a frustum, which involves knowing the length of that diagonal there and knowing your 2 radii. So we'd say radii 1, radius 1 is 2, radius 2, oops, sorry, I lied. Radius 1 is 8, and radius 2 is 12. So you could check that out if you wish. Another double check on this would be to use numerical integration on this up here to see if we got the right answer. But that is